All right, in Investigation 6A, we talked about global atmospheric circulations, and we did make note of the fact that both the atmosphere and oceans are responsible for redistributing much of the heat energy that comes in and hits the Earth's surface. Today, we're going to start talking about some of the ocean currents that we get, namely the Gulf Stream, and we're going to investigate ocean currents and how they work and what they do to help global circulation and redistribution of heat. Okay, so this is Investigation 11A. I'm going to do it in several parts. So we'll do the first little bit together where we're actually going to talk about how the investigation is going to go and kind of give you some background, and then we'll get into it. Okay, so I'm up here at the objectives. It says the ocean's a major player in the Earth's climate system, and the ocean and atmosphere are closely coupled. Huge wind-driven gyres, which are roughly circular or oblong current systems, occur in all ocean basins. And we've talked about the word gyre and pointed out that there are 5 major ocean gyres in the world, and they're just huge circulations of water. Along their boundaries, differences in density of warm and cold seawater help produce sloping ocean surfaces, which in turn generate narrow surface boundary ocean currents, such as the Gulf Stream. Analogous to rivers on land, strong ocean currents develop bends or meanders along their course. Some meanders pinch off and form large rotating circulations called eddies or rings, which can extend to considerable depths. Okay, so let me go back and kind of walk you through this. So what they're saying is differences in density of seawater is going to help produce sloping ocean surfaces, and it's going to help set up some of these ocean currents like the Gulf Stream. Okay, y'all know enough about density to know that warm water or warm air is going to be less dense than cold water or cold air. Okay? And it says analogous to rivers on land. We need to make sure you know what the word analogous means. It's like saying similar to rivers on land. Strong ocean currents develop bends or meanders. If something meanders, it kind of wanders. It doesn't go in a straight line. Okay? So it kind of wanders along their course. Some of these meanders pinch off and form large rotating circulations called eddies. Okay? So it says after completing this investigation, you should be able to explain why the sea surface slopes where warm and cold seawater occur side by side. Because remember, warm water is going to be less dense and take up more volume than cold water. Describe the development of ocean surface currents in response to water temperature and density differences, and describe how the Coriolis effect influences the direction of motion of surface ocean currents and eddies. Remember, the Coriolis effect is that apparent curvature of everything as it tries to move in a straight line because of the Earth's rotation. Okay, so let's get started. I'm down here where it says investigating pressure, and here's what we're going to do. For the first 10 or so little questions that we're going to do, we're looking at what they're going to call pressure blocks. And you may at first sort of wonder, why in the world are we playing with blocks when what we really need to be talking about is the ocean? But the blocks are going to kind of walk you through and help you understand how the differences in density in warm versus cool seawater is going to help influence some of the things that we're going to see. So we're going to use, it says, imaginary pressure blocks are used in this investigation to model sloping ocean surfaces resulting from density differences produced by variations in water temperature. Okay? Now, it's important to note that while both temperature and salinity, remember salinity is how salty the water is, while both temperature and salinity differences lead to currents, we're only considering temperature here. Okay? We will examine pressure blocks as depicted in the following figures 1 through 4. And you need to assume a couple things about these blocks. Assume that all the blocks employed in this investigation have the following characteristics. All the blocks have the same weight, regardless of their volume. So all blocks have the same weight. The base of all blocks are the same size. So the base area is the same size. And assume that the red blocks have twice the volume of the blue blocks. Okay. All right. So keeping those three things in mind, let's go ahead and answer question number 1. Because all blocks weigh the same, their masses must also be equal. Density is defined as mass per unit volume, so we know that the densities of the red and blue blocks are different because their volumes are not the same. Since the volume of a blue block is 1/2 the volume of a red block, then the density of a blue block must be twice the density of the red. Okay? Think about it this way. You have both a red and a blue block have the same amount of weight or the same amount of mass. But for the blue block, that mass is squeezed into half of the volume that you're using for the red. So it's more compact. Think about a piece of bread. You take a piece of bread and it's got a certain mass and a certain volume. Well, if you take that bread and you squish it down and you squeeze out all the air holes, you still have the same piece of bread. So you still have the same mass, but now you've squished it and it's taking up a smaller volume, so its density increased. Okay? So same mass with a small volume is going to give you a big density. Okay? Because things are more compact when their density is higher. Okay? So that's number 1. All right, number 2 says, imagine 2 blocks as shown in figure 1. The 2 blocks with the same size bases, meaning that the area of their base is the same. Okay. The 2 blocks with the same size bases are resting on a horizontal surface of a table or desk. Each block pushes down on the underlying surface with a force, its weight, that is what? Equal to or different from the downward force by the other block. Okay, well, we've got to go back and remember our 3 characteristics. All blocks have the same weight. The bases of all the blocks are the same size. The red blocks have twice the volume of the blue. All blocks have the same weight. So on number 2, each block pushes down on the underlying surface with a force that is equal to the downward force of the other block, because we've already said they both have the same weight. Okay? So we're going to select equal to. Now they obviously do not have the same volume or the same density, but they do have the same weight. Okay? All right. By definition, pressure is the amount of force acting on a unit area of surface. Pressure is calculated by dividing the force exerted on a surface by the area over which the force is applied. The blocks weigh the same and their bases have the same area, so the 2 blocks exert what? Equal or unequal pressure? Well, if they both have the same weight and they both are pushing down on the same amount of area, then they both have the same pressure. Okay, so you're going to select equal pressure on the underlying surface. Okay, and you might want to take this and highlight. Pressure is the amount of force acting on a unit area of surface, and it's calculated by dividing force by the area. Okay, remember, same weight, same area, so they're going to have the same pressure. Okay, I'm going to stop here and I'm going to do part 2 starting with number 4.